Okay.
So if I could just briefly introduce Professor Xuesong Wang from Tongji University in Shanghai, China. And his presentation title is Traffic Analysis Using Shanghai Naturalistic Driving Data. Thank you, Xuesong.
Okay. Yeah, good morning, everyone. This is Xuesong Wang from Tongji University. Yeah, my topic is related to the naturalistic driving study. Actually, we already work on this naturalistic driving study for exactly 10 years. We collect data in Shanghai from 2012 to 2015. 3 years of data collection. With these 3 years, we collected 60 drivers and more than 160,000 kilometers of data collected. And from 2015, after the data collection, we started work on the data. And the first we analyze the CNC, the crash, which means the crash and the near crash. How to check the data from the NDS data. And after that, then we analyze the pre-crash scenario and the crash condition analysis. Also, we developed the car following models and lane changing models. Use the Shanghai Naturalistic driving study. This is the first time in China we use our Chinese drivers to calibrate the driving behavior models. And after that, then we use the NDS data to calibrate the autonomous vehicle control models. And then we use the NDS data, particularly focused on the safety critical events. Particularly calibrate the responsibility sensitive safety model, which is autonomous vehicle control models for car following scenario, cutting scenarios, car to non-motorized vehicles, and car to pedestrian conflict, which are 4 major types of scenarios. During this process, AI is heavily applied for data actions, modeling, and applications. My first part is to introduce the Shanghai Naturalistic driving study. The study is started from 2012 and finished at 2015, which was 3 years. And we work with Tongji University, work with the General Motor and Virginia Tech Transportation Institute, VTTI, for this data collection. I'm responsible for this data project. We had 5 vehicles with 2 next-gen data acquisition systems. Each participant drove the vehicle for 2 months. Actually, in the vehicle, we also added a mobile line. So, for the first month, we disabled the mobile line. For the second month, we enabled mobile line, which can help us to compare before and after with this active safety system. 60 drivers of data with a total mileage of 160,000 kilometers data has been collected in three years. For the data, so we have the forward radar data. For this radar data, it can capture 8 vehicles simultaneously. For the data, for the information, which includes the position and the speed of each target. And also we had 4 synchronized cameras for the front view and drivers views and rear views, 2 drivers views and rear views, and the vehicle network data. Since we are working with GM, so it enables us to access to all the vehicle data and the GPS data and for the vehicle positions. So this is with the forward front cameras and the radar data. So we combine this together to identify the subject. So this is the camera data, the face and the front and the wheel and also the rear. So this is a very brief introduction about data. And the next part is data extraction and cognition analysis. So for this topic, we analyze the crash and near crash. First, of course, we have to extract the data from NDS, and then analyze the CNC causation. And second, we analyze the driving behaviors, and particularly driver risk, particularly compare with the questionnaire data. And third, we revised the driving behavior questionnaire, because this DBQ questionnaire was developed in international countries, which is not modified before we use it. Then based on the NDS data, we revised the DBQ questionnaire. And also we use data to develop some models to detect the distractions. For example, the cell phone use for the based on the NDS data. So this is data crash and near crash data extractions. So we use the kinematic trigger algorithms and video reductions were performed to identify crash and near crash. First, we use these triggers like the lateral motion, which means acceleration, and the position and the TTCs. And we use this to identify the event. And then after we identify it automatically, then we will validate the event manually with this criteria, like the conflict or the rapid information maneuvers and the change in subject drivers expressions. This is just used as an indication for the conflict. Based on data, we identify 530 near crash and 6 crashes were identified from this database. Then we coded this data for the event information and driver information, vehicle information, environment information, and road information, and also the contributing factors for each of the events. Then we, based on the pre-crash scenario topologies, identify this CNC event into different types. Then we applied the crash cognition analysis framework to identify the causation for all these events. This is the framework for the cognition analysis. So we consider the roadway infrastructure factors, roadway environment. These are the factors we considered for the cognition analysis. Finally, we found there are 3 pre-crash scenarios we identified in the scene. 23 pre-crash scenarios we identified in the CNCs. Rear-end scenarios, lane changing scenarios, and vehicle pedestrian, bicyclist scenarios accounted for 85% of the CNCs. So for each type of the scenario, we analyzed the data for their conditions. For example, for this rear-end type of scenarios, there are different types. For one of the types, which is pattern 3, with a major cause of CNCs with a proportion of 83, and of the 70 CNCs involving driver errors, improper brakings by drivers while falling on traveling low speed, which is the main source of errors. For each type of scenarios, we conduct this kind of analysis to identify the conditions of the event. So this is a summary of the analysis. The proportion of the CNCs associated with the road uses is about 98%, which reveals a consistent prevalence of human factors. And the CNCs are affected by the interaction between the multiple cognition factors. The most common interaction contributing to CNCs was between road users and the roadway environment. And the interaction that was involved in 50% of studied CNCs. This is the main figures of the CNCs analysis we conducted. Yeah, we also revised the DBQ questionnaires. Yeah, because for these studies, before the data collection, we just use the DBQ questionnaires. But after data collected, with the CNC data, so we realize which is not suitable for Chinese drivers. For example, the variation trend of the random driving behavior measured by Shanghai Naturalistic driving study data and matches the DBQ were not consistent for each factors, which can see from the figures, which are not consistent from DBQ score and Shanghai Naturalistic driving study data. And this is we also developed Lstm models for distraction detections. Particularly, we incorporated the attention, consider the attention mechanisms. This paper has been already published in Part C. For this analysis, we use different type of the models, like Lstm, SVM, and King models, and we found the Lstm models considering the attention mechanisms, which is the best models from all different type of the methods. Then car-following and lane changing model development. These are the papers we published in the last 10 years. So first, we developed the car-following models for urban expressways. After that, we realized the car-following behaviors are different for different type of roadways. Then we calibrated the car-following models for urban street, and then for the for expressways. So we calibrated the car-following models for all three types of the roadways in China. And after that, we used the NDS data, calibrated human-like autonomous car-following models with deep reinforced learning method. And then we use this the same data. We calibrated the safe, efficient, and comfortable velocity control models based on the reinforced learning for autonomous driving. For cutting or lane changing behaviors, we also developed the cutting models for different types of roadways, and we also analyzed the data sequence, duration, and impact factors using NDS data. So we use radar data and the camera data. We first extract the car-following period. For example, we set up this distance, like lateral distance, and the range and the duration of car-following period to select the period, the car-following period. Then we verify based on the camera data. Basically, for the car-following behavior models, for freeways, so we developed the JHR models, TIPS models, and the IDEA model, and FED and Wiedemann model. These 5 models are common car-following models, and then we compare the 5 models, and we found the IDEA models has the lowest error and the smallest standard deviation of errors. So we decided to use the IDEA models for Chinese drivers when we use this model. And this is the comparison for the car-following models for urban streets and urban expressway and the freeways. The same, we found that the IDEA model is the best for 3 types of roadways. And this is just some features of different type of the car-following models in 3 types of roadways. The design speed of the drivers was the lowest of urban street and the highest of freeways, which is consistent to our expectations. And the design time headways was the greatest of urban street and the smallest of expressways. The maximum acceleration of drivers on urban street was the 55% higher than that of urban expressway and expressways. Drivers may be more careful in car-following in complex urban street environment than in the freeway and expressway conditions. Usually, people categorize drivers I think drivers have different categories, like conservative, normal drivers, and aggressive drivers. This makes a group for different type of drivers. Actually, from the NDS data in Shanghai, we found which is maybe not right. For example, the horizontal axis are different drivers ID, different drivers ID. And the y-axis are average speed. So from this figure, we can see, yeah, for different drivers, the average speed is different. But for each drivers, actually the range of the speed is very big. So it's hard to say. There are different types of, particularly there are 3 types of drivers, which is the same for time headway and for other parameters, car-following parameters. Then we analyze what other factors influence the car-following behaviors, whether the driver's behavior or the traffic environment. So then we conduct this analysis. So from this ANOVA analysis, we can see the speed is the most significant factors for all car-following parameters, design speed and time headway, which we can see for most of the parameters, car-following parameters are significant for speed, for different speed group, and not for the driver's profile, which means the environment is the most significant factors to influence drivers' car-following behaviors. Then we use the Shanghai Naturalistic driving study data to calibrate the human-like autonomous car-following, so which is conducted 5 years ago and published in 2018. So we set up this framework and the calibrated DDPG. We use the DDPG algorithm to calibrate the human-like autonomous car-following models. So this is the model performance here. But for this model, actually, we compare different type of modeling methodologies. After that, this is just to learn the human drivers. After that, we realize for most of the autonomous vehicles, they may only consider the safety, because safety is most important, but they did not consider efficiency and the comfortableness. So we use the NDS data in Shanghai and calibrate the vehicle control models, considering the safety, efficiency, and comfortableness simultaneously. So these are the functions we used for 3 types of objective functions. So for the particularly for the chiller, which is more relevant to the confidence of passengers, which has been considered. This is for the lane changing periodic event instructions from the video data and this reader data. So we set up the rules for the event detection for lane changing. And finally, we identify more than 10,000 persons, and later we identify all cutting or lane changing event. We developed the multi-level mixed effect linear models to explore drivers and changing decision-making mechanisms under different lane changing scenarios and roadway types. Here we can see we consider the arterials and local roads and expressways and freeways. And for the factors, we consider the gaps and other parameters. The influence factors such as gap acceptance and duration for the lane changes were analyzed, and the feedback models of the drivers of following vehicles in response to the lead vehicle changing lanes were studied. And particularly, we also plotted the lane changing behaviors, and very interesting phenomena we identified was like 1 out of 5 Chinese drivers responded to lane changing with accelerating, showing this courtesy or intolerance of the lane changing of other vehicles. Finally, we introduced the control method of critical safety critical event. So these are the studies that we already published for car following maneuvers, calibrate the car following ISS responsibility sensitive safety models for autonomous vehicle car following maneuvers, and for lane changing, for cutting or lane changing scenarios, and also vehicle to non-motorized vehicle conflict scenarios, and ISS models for following vehicles, but with the NPC vehicle control. For this type of models, first we have to identify the safety critical event, which is very similar to the previous introduction. This is the event we identified in Shanghai Naturalistic driving studies. And people may know in 2017, researchers from Mobile proposed responsibility sensitive safety models with the goal of ensuring that AV will be cautious enough to not cross across and will be able to reasonably compensate for mistakes of other drivers. And there are some strengths of ISS models, which is rigorous mathematical models, and it considers the worst case scenarios and covers the three primary tasks of AVs: sensor, plan, and act, which is vehicle control. So this is the formulas of the ISS models. There are four parameters which we need to be calibrated for different type of scenarios. For this type of analysis, we use the MATLAB Simulink simulation platforms. We have to consider the vehicle, the sensors, the vehicle control. We build these simulation platforms. For these platforms, first we have to prepare the data, which means for following type of scenarios, which means following scenarios. And for all the vehicle trajectory data, we have to prepare before the simulations. And this is the simulation platforms, AV control algorithm, which also considers the sensors. And this is a simulation platform which has the calibrations and evaluation models. So first, we have to identify the safety critical event for car following. This is the radio data we identified from Shanghai Naturalistic driving study data, which have about 42% of the scenarios are real-time type of scenarios. So this is the genetic algorithm was applied to calibrate the four parameters in ISS models to make sure the minimum safety longitudinal distance formula. The two objectives are optimal safety performance and low conservativeness. So this is the calibrated parameters. This is we compared with the human drivers ACC and ISS embedded ACC, the three types, and then we found the calibrated ISS models is best in safety and in efficiency. This is how safety was measured by the total time integrated time to collision (TIT). Generally, in all events, ISS embedded and ACC managed to reduce the TIT in 73%. The driving safety of AV was significantly improved. Then we calibrated the cut-ins, the safety critical cut-in event. First, we identify the cut-in event, then use the same simulation platforms to calibrate the ISS models. These are the calibrated parameters for ISS models for cut-in scenarios. And again, we compared the ISS models with human drivers and with other type of vehicle control models. We found that ISS model is the safest among all other type of the models. So the third type are the vehicle to non-motorized vehicles. But it's more which is a very complicated type. So you can see they have a different type of interaction between vehicle and the motorized, non-motorized vehicles. For these studies, particularly, we choose the longitudinal type of the control, but later we already finished the lateral type of the conflict for the vehicle to non-motorized vehicle. So for this study, typically the avoidance algorithms were calibrated and compared. The APB, which means algorithms can provide us a stable break for the AVs, which can reduce the impact to the following vehicle. The safety performance of APB algorithm was improved after modification. So we compared the APB with AEB, so, and found finally we improved APB models. Then we identify the vehicle to detection scenarios, conflict. Then we use the same platforms, simulation platforms, calibrate the ISS model parameters for this type of conflict. Yeah, this is the model evaluations. Finally, we approve the ISS model is the best in the safety than human drivers. This study has been well recognized by Intel. I was recognized by the outstanding researchers by Intel in 2020. So with the contributions in this field, in the evaluating the roadway readiness or fitness of autonomous vehicles, and also this result has been already published in the China Industry Alliance standard technical requirement of safety assurance of AV decision-makers and IEEE standard. This is just a brief summary of what we did. So first, we collect 3 years of data, and after that, we extracted the event and analyzed the crash causation. This is the first time in China. And then we calibrated the following models and lane changing models and autonomous vehicle control models using NDS data. And also we calibrated the 4 types of ISS models for 4 types of scenarios. During this data extractions, modelings and applications, AI has been heavily applied. This study has been almost concluded, and currently we are using the new type of data. We install the radars and the cameras in our test vehicles and keep collecting data in Shanghai roadways. And this for this new naturalistic driving study data, we consider as a Shanghai naturalistic driving second phase, which has more sensors and more data. Currently, we are using this data to further calibrate the autonomous vehicle control algorithms, and particularly also for the traffic sign studies. At Tongji University, other than naturalistic driving studies, we also have 8 degree of freedom full scale driving simulators, and also we are heavily work on the traffic crash data. Currently, we develop this traffic crash analysis platforms. This platform have been used in Shanghai, in Shenzhen, and in 20 provinces and cities in China. That's my presentation. Thank you.